So today is an interesting lecture. It is like climax of what we have done thus far. So what we did is, in the previous lectures we derived conservation of mass, momentum and energy, applied non-dimensional analysis and got the non-dimensional numbers out of these equations. So when we non-dimensionalize conservation of momentum, we got Reynolds number. When we non-dimensionalize conservation of energy, we got Reynolds number, Prandtl number and Eckert number. So what we are going to do is, we will write these general equations once again, try to understand the meaning of each term, state the outcomes of this equation. Why did we derive these equations? That is the whole purpose. So we are going to address this question, why, what is the outcome of these equations for an engineer, okay, not just as a scientist. So reduce these general equations for two-dimensional steady incompressible flow, and then we will do what is called a scale analysis or order of magnitude analysis for momentum equation in order to get the hydrodynamic boundary layer thickness and skin friction coefficient, and scale analysis for energy equation for Prandtl number less than 1 and greater than 1 to get the thermal boundary layer thickness and Nusselt number, and extend this discussion for Prandtl number equal to 1. Summarize the results and get the feel of the parameters estimated. That is the plan for today's lecture. So what we will do is, we will write first the equations. So the equations are conservation of mass, that is d rho by dt plus rho of del dot v equal to 0, that is dou rho by dou t plus u dou rho by dou x plus v dou rho by dou y plus w dou rho by dou z plus of rho into dou u by dou x plus dou v by dou y plus dou w by dou z equal to 0. This is conservation of mass. Now conservation of momentum, x momentum equation is rho du by dt is equal to minus dou p by dou x plus mu into dou squared u by dou x squared plus dou squared u by dou y squared plus dou squared u by dou z squared plus dou by dou x of mu by 3 dou u by dou x plus dou v by dou y plus dou w by dou z plus f of x. Similarly, y momentum equation is rho dv by dt equal to minus dou p by dou y plus mu into dou squared v by dou x squared plus dou squared v by dou y squared plus dou squared v by dou z squared plus dou by dou y of mu by 3 dou u by dou x plus dou v by dou y plus dou w by dou z plus fy. This is x momentum equation and this is y momentum equation what we are getting. Now let us write z momentum equation. Rho dw by dou t dt equal to minus dou p by dou z plus mu into dou squared w divided by dou x squared plus dou squared w divided by dou y squared plus dou squared w divided by dou z squared plus dou by dou z of mu by 3 into del u by del x plus del v by del y plus del w by del z plus fz. This is z momentum equation. Now let us write energy equation, rho Cp dt dt equal to K into del square T by del x squared plus del square T by del y squared plus del square T by del z squared plus dP by dt plus viscous dissipation term phi, which is having, I am not going to write phi because it is a huge equation. So, I can flash that equation phi, that is phi is, so this is the phi which is having all the velocity gradients multiplied by viscosity. This is basically the viscous term. So, let us write the what are the physical significances of each of these terms. So, you can see that this is inertia force, this is pressure force, this is viscous forces, and this is body force. So, let us write that in our equation. So, what is happening here is that, so this term is inertia force, that is mass into acceleration, this is inertia force, and this is pressure force, dou p by dou x, this is pressure force, and whole of this is viscous force, this is viscous force, and this is body force. So, this is the physical significance of each of this term. Now, let us take up, and that is the same for y and z momentum equation. Now, if I come to energy equation, this is convection term, the energy transfer because of the convection, this is conduction term, and this is pressure work, and this is viscous dissipation term. Here I need to mention that when we non-dimensionalized these equations, we got here Eckert number and we got here Eckert by Re. Eckert number is equal to u infinity square divided by Cp into T infinity minus Ts. This term is important only if the flow is more than subsonic, that is supersonic flows only this is important. For subsonic flows, this term, these two terms can be neglected. They are important only in case of, because the kinetic energy gets transformed into thermal energy only in case of supersonic flows, not in case of subsonic flows. Okay. So, with that, armored with this, now the next question is, okay, so many equations are there. Why do we need these equations? What is the outcome of these equations as an engineer? What is that I gain from these equations? To answer that question, let us write what is called as outcomes of governing equations. So, now let us take up first governing equations. Let us take up first only the mass and the momentum. So, if you take mass and momentum equations, if you solve those equations with appropriate boundary conditions, so which is the case? So, simple case, let me just take, if I take flow over a flat plate, this is valid actually for flow in a pipe also, but I am taking flow over a flat plate. If you just take, there is a boundary layer in which the viscous effects are important, and outside the boundary layer there are no viscous effects, and this is the velocity profile, and the free stream velocity is u infinity. So, you have the free stream velocity with which the flow is taking place over a flat plate is u infinity, and this is my flat plate, and delta is the hydrodynamic boundary layer thickness. How do I get that? That is the thickness at which u by u infinity is 0.99 times at a location at which u infinity is 0.99 times, that is the location where you get, and this is your x and this is the length L of the plate. Okay. So, if I take this kind of situation, so if I solve the mass momentum equation, I solve it for u, v, w and p. So, I get the velocity distribution and the pressure distribution. So, using this velocity distribution and pressure distribution, I can compute, find delta, that is boundary layer thickness, and Cf, that is skin friction coefficient. So, delta is, I have written already what is delta. Cfx is skin friction coefficient, that is skin friction coefficient. You get skin friction coefficient. But the skin friction coefficient is actually the engineering necessity. So, what is that engineering necessity? I will elaborate in a minute. So, what is the use of the skin friction coefficient? What is skin friction coefficient? Skin friction coefficient is nothing but shear stress divided by half rho u infinity squared. So, tau wall is shear stress, which is varying from location to location, tau wall x, u infinity is the free stream velocity and u rho is the density. Okay. So, we know that. Now, what is the use of this Cfx and how do I get tau wall from the velocity distribution? That is mu del u by del y at y equal to 0 for a flat plate divided by half rho u infinity squared. So, using this velocity distribution, I can find the dou u by dou y and I can get Cfx. So, using the Cfx, I can calculate net force exerted by the stream on the plate. This can also be deemed as the drag force. The drag force, the net force exerted by the stream on the plate is F equal to integral of tau into area W into dx, where W is the width of the plate, that is perpendicular to this board is the width of the plate. So, you have 0 to L, L is the length of the plate, W is the width of the plate. So, you get this drag force. Now, why do I need this drag force? So, you need what is the pumping power required for blowing the velocity u infinity overcoming the skin friction, that is pumping power is equal to drag force into velocity u infinity. So, this gives you the blower capacity or the pump capacity to be utilized, pump capacity or the blower capacity. It is this engineering necessity to find this pumping power makes us to solve this mass and momentum equations to get the velocity distributions. That is the outcome of this governing equations. But then, based on what we have done, similarity analysis, we saw that when you non-dimensionalize the momentum equations, you got the non-dimensional number Re. You saw only one non-dimensional number Re, which is nothing but the ratio of the inertia force to the viscous force. So, you can, it is natural to expect that Cfx is a function of only Reynolds number. Whatever I have told for external flows, that is flow over a flat plate, is valid for internal flows as well. So, now what we will do is, we will take up what is the utility or the outcome of energy equation. If you take energy equation, okay, and for the energy equation, what is that I am addressing is, I take flow over a flat plate again, and this flat plate is maintained at a higher temperature Ts, at a constant temperature Ts. Now, flow is taking place by the free stream velocity u infinity at a temperature T infinity. Now, the temperature distribution will look something like this. So, near the wall the temperature is Ts, and away from the wall the temperature is T infinity. So, here we come across what is called as thermal boundary layer thickness, that is what we call delta T. So, how do I get thermal boundary layer thickness is that T minus T infinity divided by Ts minus T infinity, where it becomes 0.99, that is my boundary layer thickness, thermal boundary layer thickness. Now, if I solve this energy equation using, I have already got, remember I have already got from the momentum equation, solve this equation using U, V, W and P, which I have already gotten from by solving mass and momentum, you are going to get temperature profile. So, you get the temperature distribution. So, using this temperature distribution, so what is that engineering outcome? The engineering outcome is you get thermal boundary layer thickness and the heat transfer coefficient, which is represented in the non-dimensional form as Nusselt number. So, delta T is thermal boundary layer thickness, thermal boundary layer thickness, and H is the heat transfer coefficient. So, how do I get heat transfer coefficient, whose unit is heat transfer coefficient, unit is watt per meter squared Kelvin. How do I get this? H is minus K dou T by dou Y at Y equal to 0 divided by Ts minus T infinity. Using this temperature distribution, you can compute this minus K del T by del Y. So, you can get the heat transfer coefficient. So, what is the use of this heat transfer coefficient? What is this K? K is Kf. Kf is the thermal conductivity of the fluid which is flowing on the plate, not the thermal conductivity of the plate, please do not get confused. Ts is the temperature of the plate, T infinity is the fluid temperature, which I have told already. So, what is the utility of this H? That gives me resistance to the transfer of heat from the plate to the fluid, or simply heat transfer rate, plate to the fluid, that is Q dot is equal to H into surface area, that is length into width of the plate. My length of the plate is this L. So, width of the plate perpendicular to this board into Ts minus T infinity. It is this engineering necessity to find what is the heat transfer which is possible. If I blow an air of U infinity and T infinity and maintain a temperature very high, if that is the case, how much heat I can remove, that can be obtained only when I solve the energy equation, get the temperature distribution, get the heat transfer coefficient, from there you can calculate this. So, it is this engineering necessity, this engineering necessity to compute the Q dot makes us solve the temperature distribution. So, like if you non-dimensionalize the energy equation for subsonic flows, you are going to see here 1 by REPR. So, we can expect that for subsonic flows, Nusselt number is going to be a function of Re and Pr. But if supersonic flow happens on this plate, in addition to REPR, there will be Eckert number as well. This I can write on the basis of dimensional similarity. Dimensional similarity. Okay. So, now what we will do is, in the next step, as I said, we will have to reduce our equations. So, what we will write is, consider laminar boundary layer, laminar boundary layer over a two-dimensional body, that is flat plate. I am going to take flow over a flat plate. Before I take up that, let me state what are all the assumptions under which I will consider this laminar boundary layer. Okay. So, the assumptions are properties, thermophysical properties are constant, that is K, rho, Cp, mu of the fluid are constant, they do not vary, and flow is incompressible, that means my density is constant, flow is incompressible, density is constant and uniform. Okay. Then flow is steady, nothing is changing with time. Then another important thing is flow is laminar. Under these conditions, I consider flow over a flat plate. Very simple case, I consider flow over a flat plate. If I take flow over a flat plate, then things will only vary with length. Now, what happens is that in that case, so I have considered the flow happens to be two-dimensional when the flow over a long flat plate is considered. Boundary layer thickness varies only with length but not with width. So if you have taken this board, the flow is taking place like this, the flow boundary layer will vary only with length, but with the width, the boundary layer thickness is same everywhere. That is what I meant. So, now if you take conservation of mass, okay, and this is the conservation of mass equation. So, this d rho by dt term will be 0 because it is incompressible flow, density is constant and uniform, and it is two-dimensional flow. So, W and Z will not exist. So, dou W by dou Z equal to 0. So, the continuity equation reduces to dou W by the continuity equation reduces to dou U by dou X plus dou V by dou Y equal to 0. So, now let us look at how does the energy equation reduce to. In the momentum equation, in the x momentum equation, you have minus rho, dou U by dou T term becomes 0 because it is steady flow, and there will be no W because it is two-dimensional flow. So, on the left hand side you are left with U dou U by dou X plus V dou U by dou Y, and on the right hand side you have minus dou P by dou X, and this term dou squared U by dou Z squared is 0, and it is incompressible flow, that is del dot V, that is dou U by dou X plus dou V by dou Y plus dou W by dou Z is 0, and Fx, there is no body force term. So, I am left out with only these terms. So, let me write those terms, that is you have rho into U into dou U by dou X plus V into dou U by dou Y equal to minus 1 by rho dou P by dou X plus nu into dou squared U by dou X squared plus dou squared U by dou Y squared. Similar to the what we wrote for x momentum equation, and the similar logic I can throw away dou V by dou T term, dou V by dou Z term, dou squared V by dou Z squared term, and this dilation rate, and I am not considering body force. So, in that under those conditions I have U del V by del X plus V del V by del Y equal to minus 1 by rho dou P by dou Y plus nu into dou squared V by dou X squared plus dou squared V by dou Y squared. Now let us take up the energy equation. Now let us take up the energy equation. In the energy equation, you have the energy equation. So in the energy equation, dou T by dou T is 0, and you have dou T by dou Z is 0 and W is 0, and dou squared T by dou Z squared is 0, and I am considering subsonic flows. So I had told earlier itself, for subsonic flows there will be no pressure work done, and also the viscous dissipation term can be neglected. These two relate to Eckert number. So under those conditions, so I will be left out with U dou T by dou X, U dou T by dou X plus V dou T by dou Y is equal to alpha into dou squared T by dou X squared plus dou squared T by dou Y squared, dou squared T by dou Y squared. Now what are the boundary conditions? What are the boundary conditions? So based on no slip, at Y equal to 0, U is equal to 0, and impermeability, there is no permeability, that is my flat plate is impermeable, it is solid. So at Y equal to 0, it is V equal to 0, it is solid wall, and at Y equal to 0, it is T equal to Ts, that means it is constant wall temperature. Okay, now what happens at Y tending to infinity, at infinitely far away from the plate, that is in both x and y directions, that is as y tends to infinity, u is equal to u infinity and v is equal to 0 because it is uniform flow, okay, and T equal to T infinity because it is uniform temperature. So the next question is, we are going to analyze what is called, in the next class we are going to solve these equations without really solving, but we make what is called as scale analysis or order of magnitude analysis. So let us try to do this order scale analysis and order of magnitude analysis and get delta and Cfx from momentum equation and delta T and Nusselt number from energy equations for both Prandtl numbers less than 1 and Prandtl number greater than 1, and how do I get for Prandtl number equal to 1. So with this I am stopping this class. Thank you. We will get started with scale analysis and order of magnitude analysis in the next class. Thank you.